hello students, this is experiment number 3, thermal conductivity of metal rod. So here also we have to calculate thermal conductivity of metal rod. Metal rod is of aluminium material. So where is that aluminium material metal rod? We will see in this setup. Okay. So here first at outer side if we see, so this is dimmer state. Okay, blue color dimmer state to vary voltage. There is voltmeter and ammeter. Here we have arranged 80 voltage, and then through that 80 voltage current flowing 0.542 ampere. Temperature indicator, okay, and junction box. In junction box, T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, T11, T12, total 12 thermocouples are here. Okay, so where these 12 thermocouples are there, okay, we will see here. Now first, this is our setup. Here left side you are seeing this smaller diameter cross sectional red, okay, red color cross section part you are seeing here. This is nothing but your heater. Okay, inside this shell there is heater coil. Okay, after this, the middle of this portion if we see, in between this yellow band portion, this is middle of this, okay, complete setup. Inside this shell there is a metal rod. Okay, metal rod diameter, it is 0.075 meter. It is of material aluminium. Cross sectional area of this metal rod, it is 4.41 into 10 raised to power minus 3 meter square. Okay, so then outer side of this metal rod is what? So outer side of metal rod, it is glass wool insulation. Okay, fiberglass wool insulation in between outer surface and inner rod. Okay, so because to restrict heat from your metal rod to surrounding. Okay, so here at the right side, right extreme side, you are seeing this portion, it is nothing but your water jacket. Okay, so here water is flowing continuously inlet, okay, and flowing through this jacket. The jacket is inside this shell, and then outer will be towards your basin. So here this is T7 and this is T8. Okay, this is T7, this T8. Okay, T7 it is inlet water jacket, and T8 it is outlet water jacket temperature. Okay, so after before this T1, T2, T3, T4, T5, T6, where it is? So T1 it is extreme left side of this metal rod. So we assume this is nothing but AA cross section. Extreme left side it is AA cross section. Okay, so there are total 3 cross section we are assuming. First extreme left, then middle, and extreme right. So extreme left it is AA cross section. At the middle of this rod it is BB cross section, and extreme right it is CC cross section. So at AA cross section we assume T1 temperature, then T2 temperature, okay, then T3 temperature. Okay, so up to this T1, T2, T3 it is nothing but your AA. Okay, and then afterward after your T3 temperature and before T4 temperature, that means in between T3 and T4 there will be BB cross section. Okay, we assume BB cross section. So we will see in our regular observation and calculation part also. So BB cross section in between T3 and T4. So after this BB cross section there will be T4, then T5, and then T6. So T6 it is extreme right. Okay, so in extreme right at T6 temperature there will be a CC cross section. So in this way AA, BB, CC, 3 cross section we are assuming. Okay, so first we have to calculate the KCC, that is thermal conductivity at CC cross section. Okay, then we calculate KBB. Through this KCC we calculate KBB and then KAA. How this calculation part will be there, so we will later on understand. So this in this way T1, T2, T3, T4, T5, T6, T7, okay, this will be your inlet water jacket, and T8 this will be outlet water jacket. T9 and T11, So where it is T9 and T11? T9 it is at offset radius. So at offset radius at insulation part, so this is T9 temperature, so at 0.05 meter radius, okay, that is at glass wool T9 temperature will be there, 0.05 meter radius. Similarly T10 temperature, okay, so it will be at offset radius, that is 0.075 meter at glass wool, okay. So it is T9 and T10, it will be in between TAA and this will be at in between your cross section AA and BB. Similarly your T11 and T12 temperature will be in between cross section BB and cross section CC. Same radius will be for T11 the radius will be 0.05 meter and T12 radius will be 0.075 meter. So in this way all the 12 temperatures are here. So how we have to calculate the KAA, KBB and KCC? Finally the average K temperature you will calculate, average K thermal conductivity you can calculate with the help of mean of KAA, KBB and KCC. So how calculation part will be there, we will later on understand it. So first you have to calculate the KCC through this water jacket. Okay, so water jacket it is MCPDT, that is temperature difference between T8 and T7. Through that you calculate KCC, okay, with the help of your QCC. Okay, so how this calculation part we will later on understand. Okay, so in this way this complete setup will work. Okay, so in this way T1, T2, T3, T4, T5, T6, T7, T8, T9, T12 temperature you have to calculate. Same for steady state temperature, you have to take the reading in interval of 10 minutes. Okay, so same thing you have to repeat here also. So this is all about the setup for your thermal conductivity of metal rod. Thank you very much. Hello students, so this is our experiment number 3. In previous video you have seen about the setup and various arrangement. Okay, so now we see here the observation part and calculation part. Determination of thermal conductivity of metal rod. Okay, so note instructions you can see here, one side both side rule page for writing as per requirement. Left hand side blank page, draw diagram, pencil and scale use there, and write corresponding description of diagram on RHS rule page. These are strictly followed. Okay, now see about technical part here. Thermal conductivity we have already studied. Okay, this is transfer of energy from one molecule to another. Okay, and here it is possible in solid, liquid, gases, all in all medium, but mainly it occurs in solid. Okay, so if we see the unit, it is watt per meter Kelvin, and metal in general have higher thermal conductivity. Why metal has higher thermal conductivity? Because of free electron motion. Okay, so there are certain thermal conductivity written over there. Pure copper at 20 degrees Celsius 384 watt per meter Kelvin. So please remember this for general awareness only, because in interviews, various interviews generally ask this exam from mechanical person, so it is important. So pure copper has 384 watt per meter Kelvin, brass 11 watt per meter Kelvin. Okay, so all this is stainless steel, aluminum, you can see here. Okay, so we already covered this part. There are two ways through which thermal conductivity occurs here. The physics behind thermal conductivity is lattice vibration and transport by free electron. Okay, so if free electrons are there, so there will be high possibility of thermal conductivity, just like your any type of metal. If you see, so there you can see the free electron, and due to that free electron availability, there is high probability. Similarly for crystalline solid, just like your diamond, there also thermal conductivity is very high because of lattice vibration. Okay, because of their lattice structure of material. copper, aluminium, silver, these are metal, that's why these are good conductor of electricity and good conductor of conductivity also. Okay. But increasing thermal vibration come in way of transport by free electron. For most of the pure metal, thermal conductivity decreases, okay, with increasing temperature. So in certain cases, if we increase the temperature, so lattice vibration will be there, at the same time free electron motion will be there. But because we are increasing temperature, so increasing lattice vibration, at the same time transport by free electron also. So that's why decreases, what, thermal conductivity decreases, because that will create hindrance for free electron because of lattice vibration. Frequency increases there, so that's why their thermal conductivity decreases. Why? Because that will create hindrance, lattice vibration create hindrance for free electron motion. Okay. So this is one of the reason. In certain cases decreases, thermal conductivity decreases with increasing temperature, but in most of the cases K value to be constant generally for definite trend observed. Okay. So Fourier law of heat conduction we already covered. Q conduction is equal to minus Ka dt by dx, okay, where K thermal conductivity, A area of cross section, dt by dx temperature gradient. Okay. So that's why heat is conducted in direction of decreasing temperature. Why decreasing temperature? You can see Q it is equal to minus K dt by dx. Minus includes the significance there, that heat is conducted in the direction of decreasing temperature. Okay. Because thermal gradient become negative when temperature decreases with increases x. Okay. So we know that if we do the final change, so it is what, final minus initial, but always temperature flow from higher temperature to lower temperature. So low minus high if you write, so it will be negative. Okay. So that is the reason we see their negative sign. So this is about setup. Setup we have seen here. See one by one, where are the different thermocouples. This is your T1, this is your T2, T3, okay, then T4, then T5, then T6, then T7, sorry, this is T7, then T8, okay, then T9, then T10, then T11 and T12. See here, this is metal rod, okay, this is your metal rod. Here heater is there, so we have seen this is red shape, this is heater, okay, this is dimmer state, it is attached with your heater, okay, dimmer state. At the same time it is connected with voltmeter also, you can see voltage and current there with the help of voltmeter and ammeter. Now temperature junction, to see the temperatures in your temperature indicator. Okay, so here jar is there, measuring jar. Why it is required? Here water will flow from this water jacket. Right side water jacket we have seen in our experimental setup. Water will in from T7 temperature to T8 temperature here. So water will gain heat. Heat is proceeding from this heater side to this water jacket side. So heat is propagating from heater side to water jacket side through this metal rod. There is a gap in between the outer shell and metal rod. This gap is filled with insulator. Okay, so here if you see from water jacket, if T7 temperature flowing in and T8 temperature flowing out, so this T8 temperature will gain heat due to this metal rod heat, okay, at the extreme point heat. Okay, so here T7 T8, so how I can calculate QCC? So see here, these are the three sections we can see, TAA, TBB, TCC. Okay, so this is your TAA, okay, TBB, and this is TCC. Okay, in setup I have given you that direction for A, B, B, C, C. These are the three parts. So heat is flowing from this heater side to metal rod. First heat will pass from AA section, then BB section, then CC section. CC it is last. Okay, here T6 temperature is there. So when water flow from this water jacket, so it will acquire heat, it will gain heat from this right side of metal rod. So that's why how I can calculate this heat QCC. So QCC heat, it is equal to what? mCp dt. So dt means what? Temperature change in between T8 and T7, T8 minus T7. So in this way I can calculate QCC. Okay, so QCC it is equal to mass flow rate. So how to calculate mass flow rate? With the help of measuring jar. So here from this measuring jar you can collect water for particular time duration. Let us assume for 1 minute how much water will fill there. So in this way we can calculate volume flow rate. So if we have volume flow rate, so multiply with density, we can convert this volume flow rate into mass flow rate. So mass flow rate into Cp value for water, it is fixed, and then T8 temperature you can see from temperature indicator, and T7 temperature. This is nothing but your QCC. So finally you can calculate QCC with the help of this formula. Okay, so after QCC what you can do? After QCC, here you will apply, here at section CC you can apply your Fourier law of heat conduction. QCC it is equal to what? Minus Ka dt by dx. So dt by dx here at CC section, dt by dx here at CC section, dt by dx at CC section. So dt by dx at CC section. Okay, so this will see in your calculation part. Then after calculating this dt by dx CC, okay, so then again you can calculate, from this you can proceed towards your QBB. So what is QBB? QBB, see, this is QBB, this is QCC, and this is QAA. Okay, so QAA, as heat will flow from your left hand side to right hand side, it will get decrease. Okay, so QBB, here temperature your heat will be less, and again QCC will be lesser. So QBB it is equal to what? QBB it is equal to what? QBB it is equal to QCC plus heat loss, QCC plus, okay, again I will say, this is QBB. Okay, so some heat will go towards your radial direction and some heat will go towards your CC. So this is QCC, okay, and this is radial heat loss. So radial heat loss in between BB and CC. So radial heat loss in between BB section and CC section plus QCC, it is equal to QBB. Okay, so this is the conservation principle. Again QAA, so QAA it is equal to what? QAA it is equal to radial heat loss in between AA to BB, radial heat loss in between AA to BB, radial heat loss in between AA to BB plus QBB. Again I am explaining this. Let us assume heat is flowing from this QAA. So some heat will go towards your radial direction and some heat will go from A to B. So this heat is nothing but what? QBB, and this heat is nothing but your radial heat loss, okay, in between AA and BB. So this is all your calculation part also in setup. So first what you have to do here, you have to first open your water cock, okay, water inlet, and then make very less flow rate, okay, very less flow rate for steady state. Okay, again here also you have to attain steady state, so after every 10 minutes you have to take the reading. Same procedure you have to follow here also for steady state. Okay, so this is fiberglass wool insulation, this is your metal rod. Okay, so this is heater, this is your water inlet, water outlet, this is water jacket, this is your water jacket. Okay, water inlet. Okay, water outlet, this is your water outlet. Okay, so in this way this is all about the setup. Now see, again setup develop for finding K of given metal rod consisting of aluminium rod, one end of which is heated by cartridge heater, while other end provided space for water circulation chamber, as we have already discussed about this. So about temperature, thermocouple also we have seen 6 thermocouple are placed along the length of the test rod at distance of 40 mm. So it is also very important, at a distance of 40 mm. 2 thermocouple T78 are placed to read the inlet and exit temperature for water jacket. Okay, 4 thermocouple T9 T10. So T9 T10 is where, so this is your T9, this is your T10. Okay, this is similarly T11 T12. So the distance, radial distance also it is provided. So first rough calculation I will provide you so that you will understand this. Okay, diameter of metal rod it is 0.075 meter, cross section area of rod it is given, radial location T10 T12 also it is given 0.075 meter, radial location T9 T11 it is given. So half length of insulating shell considering for radial leakage it is 0.1 meter. Thermal conductivity of material filled in shell it is given 0.038 watt per meter Kelvin, it is of insulation. Okay, then distance between two thermocouple it is also given 0.04 meter. Okay, so this is our observation table. Here you have to see the temperature in your temperature indicator. At every 10-minute interval of time you have to take the reading until you will not get steady reading. Okay, so this is about your observation. Then about calculation part, same I have discussed this. QCC you have to calculate. So QCC it is equal to mass flow rate Cp T8 minus T7. Then QCC it is equal to minus KCC. Okay, so this is let us assume your rod. Okay, this is section, 3 sections. Okay, this is your QCC, this is your QBB, and this is your QAA. QAA. Okay, so some heat will loss from this radial direction and some heat will loss from this radial direction. This is the arrangement here. So okay, so QCC finally if you have, so you can calculate KCC. Okay, so dt by dx Cc, how can we split this? Dt by dx Cc, it is T8 minus mCp dt, it is okay, but dt by dCc you have to calculate. What you have to do here, if you have to calculate this dt by dc, step by step, first you calculate your QCC, then QBB, okay, and QAA. So to calculate this we have this all the formula. About your dt by dx AA, dt by dx BB, dt by dx CC, you have to plot the graph. What you have to do? You have to plot the graph. This is all about your calculation part. Okay, so to plot this graph, what you have to do here? To plot this graph, see, we have given here the draw temperature versus length plot for temperature rod to determine dt by dx. Okay, so to determine dt by dx, what you have to do? Draw temperatures versus length. So this is your temperature and this is your length. So lengthwise temperature, so thermocouple distance it is given point something 04 or something given there meter. Okay, so in that particular scale you have to make the temperature T1, T2, T3, T4, T5, T6. Okay, likewise. Then you plot the graph, and whatever slope you will get. So how dt by dx AA, where dt by dx AA will be in your 1 and 2. Okay, there you will see dt by dx AA. Similarly, your dt by dx BB in between your 3 and 4, and dt by dx CC in between 5 and 6. In this way you calculate your dt by dx AA, dt by dx BB, dt by dx CC. Okay, so finally you use this dt by dx AA, dt by dx BB and dt by dx CC in your regular equation of Fourier law. Here you will use dt by dx CC. Okay, then finally you will get KCC. Okay, now m dot, it is given mass flow rate of water in water jacket. Cp, it is constant T8 T7, you will get from your calculation, your observation. Area of cross section, it is directly given. Okay, so in this way you calculate KCC. Same similar way you calculate KBB also. Here the formula will be what? QBB, it is equal to QCC plus QRL1. So what is RL1? RL1, it is radial loss. So this is radial loss in between BB and CC. So radial loss RL radius 1. Okay, similarly this is radial loss at 2. So in this way you will calculate KBB also, at the same time KAA also, and finally the mean of this KABA plus KBB and KCC divided with 3, you will get average thermal conductivity of metal rod. So this is all about calculation part of thermal conductivity of metal rod. So thank you very much.